Hello everyone. This represents our semester project on applying discrete structures to macroeconomic data. We analyzed the Consumer Price Index (CPI) of Pakistan to uncover hidden structural relationships between cities. Typically, inflation is viewed as a simple statistic in a table, but we asked a structural question: does inflation in Karachi spill over to Hyderabad? Is the price between behavior in Sukkur mathematically closer to Lahore or Multan? To solve this, we moved beyond linear correlation and modeled the economy as a graph G of V and E. Here, our vertices are the cities, V, and our edges represent the similarity in prices behaviors over time, which is E. By treating the economy as a network, we can use graph theory to identify bridge nodes, cities that transmit economic shocks, and hubs that dictate national trends. Now, let's dive into the discrete mathematical modeling. We first defined a vector space model. Each city is represented by a price vector for a specific category, like food, utilities, over m months. We normalize these vectors to unit length to focus on the pattern of price changes rather than the raw magnitude. To define the edges, we used cosine similarity. This calculates the dot product of the two normalized vectors. A value of 1.0 means identical price fluctuation patterns, while 0 implies orthogonality or no correlation at all. Crucially, we formalize this as a binary relation R. We proved that this relation is reflexive. Every city is similar to itself, creating self-loops, and symmetric. If Karachi is similar to Lahore, then Lahore is also similar to Karachi. This symmetry justifies our use of undirected graphs for the network analysis. The topology of these graphs changes based on our similarity threshold tau. Here is the food staples network. You can see it is highly dense. This indicates that food prices converge nationally because these goods are highly regulated and easily traded. Contrast that with the utilities network. It's sparse. Look at Quetta. It is isolated. This discrete structure reveals that utility prices in certain regions rely on local infrastructure rather than a national grid. The graph structure physically represents economic isolation. We empirically determined that a threshold of tau 0.70 was optimal. Anything lower created a complete graph, a click, which gives no insight, while anything higher fragmented the graph too much. Once the graphs were built, we needed to measure influence. We calculated four centrality metrics for every node: degree, closeness, betweenness, and eigenvector centrality. However, a single metric is often misleading. We introduced a novel weighted centrality aggregation strategy. We combined these four metrics into a single influence score using distinct weighting techniques.
The most sophisticated technique was entropy-based weighting. We calculated the xenon entropy of the centrality distributions. If a metric had a low variance, meaning it looked the same for every city, it was assigned a low weight. We prioritized matrices that were volatile as they held the most discriminative power. The results were striking. Understanded weighting, Karachi and Lahore dominate as expected, but using entropy-based weighting, Quetta and Peshawar entered the top ranks. You may ask why. Because they act as critical bridges nodes, connecting different economic zones even if they were not the biggest markets. We applied order theory to analyze temporal stability. We defined a partial order relation based on the subsets of edges. We asked, is economy of 2019 a subgraph of 2020? If yes, we mapped it accordingly. We verified the condition for the partial order, reflexivity, antisymmetry, and transitivity. This allowed us to construct Haze diagram. The diagram shows the economic flow of integration. If 2019 connects to 2020, it means economic relationships established in 2019 were preserved and expanded in 2020. Breaks in the chain indicate structural rifts or economic shocks.
Sleepless beats.
Implementation. All of this was implemented in Python using Pandas and NetworkX library. Here is our compute metrics function. It pivots the raw data into vectors, calculates the cosine similarity matrix, and dynamically generates the graph edges based on our threshold. We also built an interactive dashboard. This tool allows policymakers to manually adjust the weights for the degree of betweenness to see how ranking of the cities changed in real time. It effectively turns our discrete model into a decision-making model. Now moving on to the conclusion. In conclusion, this project successfully bridged the gap between abstract discrete structures and real-world economics. We demonstrated that Pakistan economy is not a single unit but a collection of clusters defined by complex relations. We learned that the relation defines market integration, graph centrality defines economic influence, and partial orders reveals temporal stability. We have moved from viewing prices as simple numbers to viewing them as a complex, interconnected discrete system.
Sleepless beats. Sleepless beats.